This is lecture number 2 under adders. Last class we discussed half and full adders. Today we are planning to discuss ripple connection of adders and its problems. Then carry look ahead adder to solve the problems of ripple adder followed by BCD adder. Okay, right. So last class we completed the discussion of full adders, right? And we understood that in full adder, the sum expression was A XOR B XOR with C, and this C was my input carry C, and carry out was the product of individual bits, right? And this C is actually carry in, right? So let us see how many gates are required to implement a sum output. Suppose we are implementing the sum output using and or not gates. Okay, so let us see how many logic gates are required. Right, the sum output was A XOR B XOR C. Right. So if A XOR B XOR C is nothing but let us say uh, X bar C plus X C bar with X equal to A XOR B, right? X bar C plus X C bar is nothing but X exclusive or C. And if we are substituting X equal to A XOR B, then that will be X or B XOR C, right? And X equal to X or B implies X complement will be the XNOR function, that is A bar B bar plus AB. That is in place of X complement dot with C plus A XOR B is equal to X, that is nothing but AB plus, so A bar B plus AB bar, A bar B plus A bar dot with the C complement, right? So if you are taking C into the bracket, that is nothing but A bar B bar C plus A B C plus A bar B C complement plus A B bar C bar. If you're observing individual terms, you can see that odd number of ones, right? This is 001, 111, 010. This is 100, odd number of ones corresponding to sum equal to 1, right? So to implement this function, some output of my full adder, right? I request AND gate, right, to take the protect, right? Take the protect, right? 1, 2, 3 AND gates are required, right? Okay, and we should take the OR operation between its output, right? Prior to that, I should implement A bar, B bar, and C bar, right? So I should get A bar, B bar, C, etc. up to 1, 2, 3, 4 terms. So I should use another AND gate. Right? In last input, let me write it as A, B bar, C bar. Right? In this fashion, I should connect to produce a sum output. Right? So please listen carefully. We are talking about time delay required to produce a sum output. Right? If A, B, C inputs are readily available, they are ready, and how much time it will take to produce a sum output. right? And that is very simple. First, we should produce complement of the inputs, right? For that, we require one gate delay. Okay, one gate delay for producing complements. Depends. Less. We should produce the AND gate output product terms, and all these AND gates are operating parallelly, right? So this is second gate delay. Okay, so one AND gate delay. So simply one gate delay, right? One corresponding to inverters, another one corresponding to AND gate. Since all are connected in parallel, I should count only one gate delay for AND gate. Similarly, last gate is OR gate. I require another one gate delay. So the other way to produce a sum output, we require three gate delays. Okay, three gate delays. And what about carry out? This is my carry out, right? Carry out is very simple. We should produce the protect terms first. Okay, protect term first. For that, I should use AND gates, right? Three number of AND gates in parallel, and I should take the OR operation between individual outputs. So AP plus BC plus SC, right? So I have to use two level gates. One is AND that corresponding to a delay of one gate delay, and another gate in series with AND array, that is OR gate, another gate delay. So effectively for sum, I have three gate delays. Okay. For carry, I have two gate delays. Okay. Right. Or the other way, if carry input is ready, if carry input is ready for a full adder, it will take two gate delays to produce carry out. Similarly, if carry input is ready, a full ladder will take three gate delays to produce some output, right? So along with the carry input, the input bits also should be available, right? If both inputs and carry in are available, a full adder, a full adder, and full adder maybe in the first stage, maybe in the second stage, maybe in the nth stage. If you are cascading, connecting one after another, doesn't matter. If everything is ready, a full adder will take two units, two gate delays to produce a carry out. And if everything is ready, a full ladder will take three gate delays to produce a sum output, right? Is that clear? That is a basic thing you should understand, right? Based on the logic expression of carry out and sum out, right? Is that clear? Done, right? Based on the logic expression of sum out and carry out, two gate delays and three gate delays to produce carry out and sum out, right? Okay, right. So then let us connect full ladder one after other so that it will act as a ripple, ripple carry adder, ripple carry adder. And the ripple carry adder may have different number of stages, right? Two stages, three stages, four stages, right? If you are adding four digits at a time, you should use four stage of full ladders connected one after the other, right? So first stage, I'm writing it as a full ladder. first stage full adder. Okay, it will receive LSB inputs, right? Let us say A0 and B0, and it may receive a carry input also, C0. And as we discussed, a full adder will have two output lines. Some output, I am calling it as S0, and a carry out. Carry out, I am calling it as C1, right? And that is connected to the second full ladder corresponding to second digit, right? And I'm calling my second digits as A1, B1, and I will have someone corresponding to second stage full ladder, right? So this act as a carry in for the second stage. Again, it will produce a C out. I'm calling it as C2. That is connected to the carry in of my third stage. Get connected to carry in. And this is also a full adder. And let me mark the input digits as A2 and B2. And it will produce a sum output that is S2 corresponding to A2 and B2. Again, I will have another stage. I'm going for fourth stage. Fourth stage, right? Output carry, I'm calling it as C1, C2, and C3. That will be input carry of my fourth stage. Fourth stage input digits, let me call it as A3 and B3. It will produce sum 3 corresponding to A3 and B3. And I will have a carry out. I will call it as C4, right? So if you are cascading like this, for the time being, I have connected 4 number of stages, right? The question is about what is the worst case delay to produce a sum output or a carry output, right? So we said that to produce a sum output, we require 3 time units, right? Or 3 gate delays. So I'm calling it as 3 times T. T corresponding to 1 gate delay, or I will use TD, T corresponding to delay. And we also said for producing a carry out, requires 2 times the gate delay, right? The gate delay I'm taking as TD for all logic gates, right? Then to produce a second sum output, right? My carry in should be ready. That will be ready after 2 time delay. Once it is ready, I request another 3 time delays. So 2 plus 3, that's equal to 5 time delays are required to produce the second stage sum output, right? And C2, carry out of the second stage, also requires 2 more extra time delay, right? Its carry in is ready at 2 time delays. So 2 more. So for TD, my C in to the third stage will be ready, right? Right. Once carry in to the third stage is ready, that is ready by a time interval for TD, I require another 3 time delay to produce some output. So it is nothing but 4 plus 3, that's equal to 7 time delays, right? And once carry in is ready, my full adder will take 2 more intervals to produce carry out. So my carry in, sorry, carry out is ready after 6 time delays. 4 plus 2, 6. Once that 6 time delay is available, or my C3 out of third stage, C3 is available, that is carry into the fourth stage. Once it is available, I request another 3 time delays, that is 6 plus 3 equal to 9 time delays to produce some output, and 6 plus 2, 8 time delays to produce final C4 This is the worst case situation. That is, carry C0 propagates to the output of first full adder. That is again propagated. That is again propagated, right? And it appears at the final output. There is a worst case, lengthy path when carry in, first carry in propagates the all the way around the fourth stage output, that is C4 here. Okay, so if we are connecting like this, we require 9 TD for producing a sum output and 8 TD for producing a carry, final carry out, right? For n equal to 4 number of stages, right? Okay, let's copy this. Then we'll get into what happens if I am having 8 number of stages, or let us say if I'm having n number of stages. Okay, is that clear up to this point? This connection is called a ripple connection because carry ripples through each and individual stages. Right. Right. Copy this. Then we'll get into fifth, sixth, eighth, or nth stage cases. Right. Okay. Right. Then look at sum output. Right. Uh, if we are having only one stage, right, one stage, let us say n equal to 1, right, the sum will be available after 3 gate delays, right, 3 GD, right. If you're going for second stage, n equal to 2, okay, we are trying to add 2 digits, A0, A1 and B0, B1. So we should use 2 stages. Then my delay is increased to 5 times GD. If n equal to 3, the gain increases to 7 times GD. If n equal to 4, it is nothing but 9 times GD. Right. I'm concentrating on some output because the time taken for producing some output is greater than producing respective carry out. Right. So that is nothing but you can simply write it as the total delay. Total delay is a function of number of stages, right? Right. So total delay t equal to, if n equal to 1, it should be 3. N equal to 2, it should be 5. So you can write it as adding a constant 3 with n minus 1 times 2. 2n minus 1 plus 3, that many gate delays, right? So if n equal to 1, 1 minus 1 will be 0, we'll get 3 times dt. If n equal to 2, 2 minus 1 into 2, 4, sorry, 2 minus 1 is 1, 1 into 2, 2 plus 3, 5. N equal to 3, 4 plus 3, 7. N equal to 4, 4 minus 1, 3, 3 multiplied by 2, 6 plus 3, 9. Right. So if you are having 128 number of bits, then the delay will be proportional to 2 times 127 plus 3, that many gate delays. Right. If you're having a cascaded adder or a ripple carry adder with 128 stages, you'll have 2 times 127 plus 3, that many gate delays. Right, very good. Aravind also initially specified 3 plus 2 n minus 1 TD, right? Very good. Right. So actually the delay increases exponentially or as a function of number of digits, right? As the number of digits increases, number of bits increases, the delay to produce some output as well as carry out both increases, right? So the adder will have a poor performance with respect to its speed of operation, right? So if you are connecting the serial adder or a ripple carry adder along with your processor, and the processor will be treating all its devices synchronously, right? The processor will give second set of inputs only after a time interval of 2 times n minus 1 plus 3 times gate delay, right? Or the other way, to produce a proper sum, the processor should wait before applying second set of inputs. After an addition, second set of input, it should wait for at least 2 times n minus 1 plus 3 times gate delays, where n is the number of adders we are having in the ripple adder, right? So it's a slow device. It will take much time to produce the proper result if we are increasing the number of stages, right? Or if we are increasing number of bits to be added, right? Clear? This is okay, right? The alternative is carry, look ahead adder, right? Carry, look ahead adder. Right. George Joseph is asking another query. Can we write 2n plus 1 times time delay? 3 plus 2 minus 1. That is also correct. That is also correct. Right. So if you're adding 3 minus 2, you'll get a 1. 2n as such. So 2n plus 1 times td. That is also right. Okay. Let me add that also. That is equivalent to, right. Thank you for your input. 2n plus 1 times td. That is also right. Total delay. Both are correct. Thank you. Okay. Right. Okay. So carry look ahead adder. Right. In carry look ahead adder, what we are trying to do is here we should wait for carry out. Right. Carry out. Carry out. Then only the second full adder able to operate so that it produces a valid sum output as well as carry output, right? So in carry look ahead adder, we will produce a logic expression based on inputs, okay? So that along with the inputs, first carry output as well as second carry output, third carry output, etc., etc., nth carry output, all are implemented using logic gates simultaneously, right? We should not wait for carry out from the previous stage. Instead, we will connect the carry out directly to the carry in of respective stages by deriving the respective carry outputs, right? So let me make it clear. So in the last case, we have to wait for carry out from the previous stage. Here, what we'll do is we'll connect full adders like this, right? Like this, 4 stages, and carry in, we will connect directly. This will be C0. We'll implement using a logic, and that carry will connect to the second full adder. So this is my C in, this is my C in. Another logic that produces a proper C in for the third stage. Another logic that will produce C in for the fourth stage. Of course, first stage C in is readily available. And this logic will be accepting C0, A0, B0. Here again C0, A0, sorry, here it is A1, B1, A1, B1, or let me write all inputs A0 to A3, then it is perfect. Then C0, A0 to A3 along with the B0 to B3, right? B0 to B3, right? Here also carry, first carry in, then A0 to A3, all A digits, followed by B0 to B3. So we'll use separate logic to produce carry out or carry in for the higher stages. Right? We will not wait for this carry out. Right? That will take time. Instead, directly from the inputs C0, A0, B0, A1, B1, A2, B2, A3, P3, will generate respective carry outputs. So this was my C1, this was C2, this was C3. And finally, to produce C4, again, I will use another logic that will accept C0, then A0 to A3 as earlier, then B0 to B3, right? And that produces a carry out that is called C4, right? So all C4, C3, C2, C1 are readily available, similar to the first carry in C0. Then these full adders need not wait for their input carry, right? We'll use separate logic to forecast or to predict the carries other than the carry input of the first stage, namely C1, C2, C3, and C4, right? And that we'll see how to generate it. Okay, right. In full ladder, we said that the initial or the first carry or C in propagate to C out if A and B are different, and that particular stage produces a carry out if both its inputs are equal to logic 1, right? A equal to B equal to 1, that stage will generate the carry out. If A and 0, A and B are different, that stage will allow the input carry to propagate as its own output carry, right? And we defined two functions, carry generating function G and carry propagating function P, right? And we arrived a famous expression that is C out from a first stage is nothing but the carry generated from that stage or the carry propagated, its input carry propagated. Two choices only, right? If its inputs are A, B are equal to 1, 1, it will definitely generate the carry out. And if the input bits are different, that particular adder, full adder, allows the input carry to propagate. So that C out is same as C in, right? Right? Okay. So if you're comparing with this, your old adder, if you're writing for C1, right? C1 carry out of the first stage, right? C1, listen carefully, C1 equal to two options. If A0 and B0 are 1, it will generate it, right? That generating function, I'm calling it as G, A0 and B0, so I will call it as G0. And C1 will be equal to C0 if A0 and B0 are different or propagating function, I will call it as P0, right? So C0 will be propagated to C1 if P0 equal to 1 or A0 and B0 are different. And C1 will be definitely equal to 1 if G0 equal to 1 or A0 and B0 are equal to 1 simultaneously. right? So I can easily write it as C1 equal to generated carry, that is G0, plus the propagated carry, and the propagated carry is nothing but C0, carry input to the first stage, right? And that is nothing but G0 is what? A0, B0, or I will write it as G0 itself. Otherwise, it will be lengthy. So G0 is nothing but A0, B0, and G0 is nothing but A0 dot B0 protect, and B0 is nothing but the XOR operation between bits A0 and B0, right? Then I'm trying to write the expression for C2. C2, right? What is C2? C2 is the carry out from the second stage, and its carry in is nothing but C1, and its input bits are A1 and P1, right? So C1 is nothing but G1. That stage may generate the carry, or that stage will allow to propagate the carry, and that carry input is nothing but C1, right? C1. So if you're expanding this, this will become G1 plus P1 C1. C1 is this expression. So it will be P1 G0 plus P1 P0 C0, right? So it's readily available. Look at the expressions. G0 plus P0 C0. C0 is readily available. P0 also will be readily available because P0 is the XOR operation between A0 and B0. G0 is also readily available. There is AND operation between A0 and B0. So if A0 and B0s are available, plus one gate delay will produce G0 and P0. And we have one OR operation, right? So once P0, C0 and G0 is ready, it will produce G0 plus P0, C0. So carefully look at this. This is an AND function. To produce that AND function, we require one gate delay, one GD, okay, to produce that AND operation, right? To produce OR operation, I request another one time delay, right? Meanwhile, I should produce A0 dot B0 and A0 XOR B0, and that I can produce parallelly, right? I can connect A0 and B0 to the AND gate. I will get A0 B0, that is my G0, and I can use one XOR gate to produce my P function P0, that is A0 XOR B0, that is equivalent to P0. So once A0 and B0s are ready, one gate delay to produce P0s and G0s, then another gate delay to produce the product P0 and C0. Again, one more gate delay to produce the OR operation between G0 and the product P0, C0. Right, so I will write it as 1 plus 1, 1 plus 1 plus another 1. So the first one is corresponding to G comma P. Then second one corresponding to AND operation. Third delay is corresponding to OR operation. Right. Once AND output is ready, then only I can OR it. Right. So let me draw it. P0, C0 will take AND first, then OR with G0. So it's a two-level circuit, right? Two level. One gate delay here, another one gate delay here. And to produce P0 and G0, we require another gate delay. So a total of 3 gate delays. So 3, right? So similarly, what about C2? C2, I have again AND operation here, AND operation here, right? These two AND operations, I can do it simultaneously, right? So let me draw the logic diagram again. First, I'm taking the last term, that is AND with the three inputs, that is P1, P0 and C0. Then AND with the two inputs, that is P1 and G0. Then again AND with the, sorry, then again OR with the three outputs are connected to the input of OR, right? So here one gate delay here AND operation. After that, one gate delay here for OR operation. Before that, to produce P1, P0, G0, I request another one gate delay. So again, it is three gate delays. No change, right? Single stage, we requires three time delays. Two stages, then also for carry out, it is three time delay. Our problem was the carry input to the next stage will get delayed, so that some output will also get delayed, right? Now we are readily connecting the carry outputs. So C1 will be available after 3D, 3TD, C2 also 3TD seconds, right? So the adders need not wait for their carry in, right? Both cases, both carry inputs are available after three time delays, the moment inputs A0 to A3 and B0 to B3 along with C0 are available, right? Similarly, if you are extending this, if you are going for C3, C3 is nothing but that stage input, they are A2 and B2, so it can generate a carry G2 plus the stage will propagate its input carry, that is P2 dot its input carry is nothing but this one, C2, right? Third stage input carry is C2, input carry is C2, that produces C3, right? So I'm writing for C3, input carry is C2, right? That is same as G2 plus P2 times C2, and C2 is nothing but G1 plus P1 G0 plus P1 P0 C0, right? So that is nothing but G3, sorry, G2 plus G2 plus G1 P2, or let me write P2 G1, P2 G1 plus P2 P1 G0 plus P2 P1 P0 and C0, right? Look at C3 expression. Again, I have product term and a sum term. So to produce this product, I request one gate delay. Same gate delay for this because I can operate parallelly like this. I will operate parallelly, right? So to get a product, I request one gate delay. To get OR operation, I can use one OR gate, multiple input. That will constitute another one gate delay. And as I said earlier, to produce P1, P2, P3, etc., G0, G1, G2, G3, etc., I request another gate delay. So again, this is a 3 time delay. It is not increasing as the number of inputs are increasing, right? And finally, if you're writing for C4, C4, you will write it as G3, third stage may or fourth stage may generate it, right? This is A3 and B3, so G3, G3 plus P3, C, its input carry is C3, right? P3, C3, right? That is equal to G3 plus P3 multiplied by C3. What is C3? C3 is G2 plus P3. The second term is P2 G1. So P3 P2 G1. The third term is P2 P1 G0. So P3 P2 P1 G0 plus the last term is P2 P1 P0 C0. So it should take a product with P3. So P3 P2 P1 B0 and C0. Here also, if you're observing this expression, I have to get a product term, AND gate, another AND gate, another AND gate, another AND gate. But all these AND gates I can connect in parallel. So that will constitute one time delay only. And 1, 2, 3, 4, 1, 2, 3, 4, 5 terms to be added. So an OR gate with 5 inputs, right? So another time delay, GT. And to produce P3, G3, P2, G2, etc. up to P0, G0, and C0, I require another gate delay. So again, here it is 3 time delay, no change. So in carry look ahead adder, the time required to produce carry out is independent of the number of stages we are connecting together or the number of bits. Right. So as the number of digits are increasing in my ripple carry adder, the time delay was increasing, but here it is constant delay to produce all carry outputs, right? C1, C2, C3, etc. up to C4. Right? Is that clear? So that is the beauty of carry look ahead adder. Done? Clear? Please copy this. So in these blocks, actually, we are implementing different circuits. Okay, for C2, for C3, for C4, right? These logics, we will be implementing inside this, right? By taking A0, B0 up to A3, B3, and C0 as the inputs, right? So that is what is a carry look ahead adder. Clear? Any queries? The fundamental thing is that for to produce a sum output, we require 3 gate delays. To produce a carry out, we require 2 gate delays. Right? Based on that, we calculate the total delay of a serial adder or a ripple carry adder. Then we understood that time increases as number of bits increases. Then we implemented individual carry outputs using separate circuits, separate logics, and that output is directly connected to the carry in of my respective adders. Of course, the second technique, that is carry look ahead adder, will increase the hardware complexity, but the advantage is that the delay is getting reduced significantly, right? It's a constant independent of the number of bits, right? Is that clear? Please respond. Please respond. I did this very slowly because most of the classes I used to repeat the entire explanation. So I did slowly. Is that clear? Any queries? Okay, right. Right. Okay. Right. Then the obvious question is, what is the size of the logic gates required? Right. So here we were trying to add how many digits? 4 digits. Right. We were trying to add 4 digits corresponding to C1, C2, C3, and C4, right? 4 digits. And the C4 is called carry out or overflow, right? Corresponding to overflow, right? So to generate individual carry outputs, right? In the case of a 4-bit adder, we request 1, 2, 3, 4, 5 number of inputs for OR gate, right? OR gate with the 5 number of inputs, right? Similarly, what about AND gate? Look at this here. We are having AND gate with more inputs, right? So 1, 2, 3, 4, 5. So your AND gate also should have how many number of inputs? 5 inputs, right? We are trying to implement a 4-bit adder, and we understood that we require a logic gate with 5 number of inputs. So in general, we require n plus 1 number of inputs for both the AND as well as OR gates, right? The highest number of inputs are 5 numbers for both AND as well as OR gates. Okay, that also you please keep in mind. Then carry look ahead adder. Okay, right. And in the first diagram, I have used a full adder. Instead of that, if the carry input C0 is absent, you can make use of half adder also, right? If you are not having a carry in, there is no preceding stage, then you can make use of an adder with 2 number of inputs only, that is half adder. Or if C0 is absent, then you can connect a logic 0 if you are using a full adder. Okay, so first stage can be an half adder. Right. And in your carry lookup adder, what is the worst case delay to produce last sum output? Let us say S3 out. S3 is my last sum output, right? S3 is my last sum output, MSB, right? So in your carry lookup adder, how much time it will take to produce a valid S3, worst case delay? How much it is? S3 is the output of that full adder, last stage adder. S0 to S3 was the sum output, right? S0, S1, S2, and S3, right? So how much time it will take to produce a valid S3? How much time delay? How much it is? Right. George answers 6 times delay, right? Very good. All carry outputs are available after 3 time delays in my carry look ahead adder, right? All are 3 time delays. Look at this, 3 time delays, 3 time delays. Okay, so once C3 is available, right? C3 is my input to the final adder. C3 is the input, right? Once the C3 is available, everything is available. How much time it will take to produce a sum output? We said it is 3 for a full adder, right? So 3 TD plus another 3 TD will get 6 time delays. As George said, 6 time delays. Is that clear? For S2 also, 3 plus 3, 6 time delays. S2 also, we require 6 time delays, right? But for S0, we require only 3 time delays because it C0 is readily available. So S1 onwards, we require 3 plus 3, 6 time delays. 6 time delays because E1 requires 3 t plus another 3 will get 6. It's independent of number of digits, right?